Hey everyone, and welcome to another deep dive. Today we're strapping on our safety goggles and diving headfirst into the fascinating world of chemistry.
And we've got some pretty interesting source material to work with today too. We're going to be cracking open a couple of high school chemistry textbooks.
It's like Chemistry 101, but way more fun, right?
Exactly. And way less homework.
Okay, so what exactly are we going to be uncovering today in these textbooks?
Well, we're going to be exploring the fundamentals of chemical reactions. It's amazing to think that chemistry isn't just happening in some lab, It's literally happening all around us constantly.
It's like this nonstop chemical party that we're all invited to, right?
I like that, yeah.
Okay, so let's break this down. When we talk about chemical reactions, what are we actually talking about? Think of it like a chemical reaction is basically a process where, like elements and compounds interact with each other to create something totally new.
So like baking a cake, except instead of flour and sugar, we've got like hydrogen and oxygen or something.
Exactly. It's like a chemical recipe.
Yeah.
And to represent these reactions, chemists use chemical equations, which I know can seem intimidating at first,
Yeah.
but they're really just like a shorthand for chemists to describe these reactions.
It's like their own secret code.
In a way, yes. But don't worry, we're here to crack the code together.
Okay, I'm ready. So, tell me, what are the key elements of a chemical equation? What do they tell us?
Well, think of it like a recipe, right? You've got your ingredients and you've got your finished dish. In a chemical equation, the ingredients, the things we start with, are called reactants. And the final product, the thing we end up with, is, called the product.
Makes sense so far, but what about that arrow in the middle?
Ah, yes, the arrow. That arrow is super important. It's not just a random arrow. It's telling us the direction of the reaction, how those reactants combine and change to make the product.
Got it. Reactants on one side, products on the other, and that trusty arrow showing us the way. But chemical reactions, they're not all just baking cakes, right?
You're right. There's a whole bunch of different types of chemical reactions. One of the most basic types is a combination reaction, which is exactly what it sounds like.
Two or more substances combining to make a new one, like our cake analogy.
Exactly.
Yeah.
A perfect example of this from our textbook is burning magnesium.
Burning magnesium. Okay. So how does that work?
Well, you take magnesium, that's our first reactant.
Yeah.
And when you expose it to oxygen in the air, that's our second reactant, and add a bit of heat, they combine to form magnesium oxide.
Magnesium oxide.
Yes, a new substance entirely. And a cool byproduct of that specific combination reaction is a super bright white light.
Like a chemical light show.
Pretty much.
That's so cool. Okay, so we've got combination reactions where things combine, but what about when things break down?
That is a decomposition reaction, which is essentially the opposite of a combination reaction.
So more like unbaking a cake.
Something like that. One substance breaks down into two or more simpler substances.
Okay, got it. Do our textbooks have any good examples of those?
Definitely. One that comes to mind is heating ferrous sulfate. You know those beautiful green crystals of ferrous sulfate?
I think I've seen those before, yeah.
Well, when you heat those up, they decompose, they break down into a few other substances. Iron oxide.
Wait a minute, iron oxide, isn't that just rust?
Exactly.
So what you're telling me is that rust is a result of a decomposition reaction? I had no idea.
It's happening all around us, all the time.
Yeah.
Even in something as simple as rust forming, there's this whole chemical process going on behind the scenes.
So cool. Okay, so we've got things combining, things breaking down. What other kinds of chemical reactions are out there?
Well, we've also got displacement reactions. Now imagine this. You have a game of chemical musical chairs where one element gets bumped out of a compound and replaced by another. It's kind of like a chemical battle for dominance.
Okay, so give me an example of this chemical battle. What does it look like?
Okay, so picture this. You've got an iron nail, right? And you dip it into a solution of copper sulfate.
Okay.
Now, iron is more reactive than copper, so it's basically going to muscle its way in and displace the copper. And what you'll actually see is that iron nail becoming coated with a reddish-brown layer because the copper is being deposited onto the nail.
It's like a chemical heist. Iron snuck in and stole copper's spot.
Pretty much.
Gosh.
And the solution itself, that copper sulfate solution,
Yeah.
it's going to start to lose that vibrant blue color as the copper ions are being replaced by iron ions.
Wow. So it's like a visual indicator that a displacement reaction is taking place.
Exactly.
Okay, so we've got combination, decomposition, displacement. Is there anything else?
One more. We've got double displacement reactions.
Double displacement. So if displacement is like chemical musical chairs Is double displacement like a chemical square dance or something?
That's a great way to put it. Think of it as ions switching places instead of people.
Yeah.
Deuce doing and all that.
Mm-hmm.
One example from our trusty textbook is the reaction between sodium sulfate and barium chloride. You mix those two solutions together and bam, you get this white, cloudy substance forming.
What is that cloudy substance? Some kind of chemical smoke signal?
Not quite. That, my friend, is called a precipitate.
A precipitate?
Yes, and it's a telltale sign that a double displacement reaction has taken place.
So in this case, the precipitate is...
barium sulfate, to be exact.
Got it. Barium sulfate, our chemical guest star. Okay, so let me get this straight. We've got our 4 main types of chemical reactions: combination, decomposition, single displacement, and now double displacement. It's like we're learning the steps to a chemical choreography or something. But all this talk of reactions, it makes me think about the substances themselves, the ingredients in our chemical recipes, specifically acids and bases.
Acids and bases, they're everywhere.
I know, right? And they're not always as obvious as, a big bubbling beaker in a lab.
Definitely not. Think about it, though. Have you ever, gotten a little crazy with the hot sauce and needed some antacid relief?
Oh, tell me about it. I'm a big fan of spicy food, maybe a little too much sometimes. So is that antacid action a chemical reaction then?
You bet it is. It's actually the neutralizing power of bases coming in to save the day.
Okay, so bases to the rescue after a spicy food adventure. But how do we even know if something's an acid or a base? I mean, aside from the whole setting my mouth on fire thing.
We're not going to go around tasting everything, right? That's where indicators come in. They're like our little chemical detectives telling us what's what.
Like litmus paper. I remember that from our textbook.
Exactly. Litmus paper is a classic indicator. It's like a mood ring for acids and bases. You dip that red litmus paper into a solution. It turns blue. You've got yourself a base. Blue litmus paper goes red. It's an acid.
So it's all about the dramatic color reveal.
Pretty much. But we don't always need fancy litmus paper. We've got everyday indicators right in our kitchens.
Oh, really? Like what?
Ever notice how turmeric stains like crazy? Well, it turns out turmeric is not just a spice. It's a natural indicator. You get turmeric on something, and it turns this reddish brown. That means whatever it touched is basic.
So that's why soap works so well on those turmeric spills. The soap must be basic and neutralize the turmeric, making it easier to clean up.
You got it.
Okay.
Chemistry coming in clutch in the kitchen. But let's go a little deeper. What exactly makes something acidic or basic at the, molecular level?
Let's do it.
So it all comes down to these tiny little things called ions. Acids release hydrogen ions. H is how we write it when they're dissolved in water. Bases, on the other hand, they release hydroxide ions, OH, when they're in water.
Okay, so acids are all about the H and bases are team OH. It's like a chemical face-off.
I like it. And the more of those hydrogen ions you've got, the more acidic a solution is. More hydroxide ions, the more basic it is.
So how do we measure that? Is there a chemical scorecard for acids and bases?
There is. It's called the pH scale.
The pH scale?
Yeah. Think of it like a measuring stick. It runs from 0 to 14 with 7 smack dab in the middle as neutral, like pure water. Nice and balanced.
Makes sense. So what about the numbers on either side of 7?
Anything below 7 is acidic, and the lower the number, the stronger the acid. Lemon juice, vinegar, battery acid, if you're feeling dangerous, they're all down there in the acidic zone. Above 7 is basic, and the higher up you go, the more basic or alkaline it gets. Baking soda, soapy water, they're hanging out on the basic side of the scale.
So the pH scale is all about balance, finding that Goldilocks sweet spot.
You got it. And this whole balance thing is super important, not just in a chemistry lab, but in everyday life too.
Oh, I bet. Our bodies probably need things to be at a certain pH to function properly, right?
You're right. Our blood, for instance, has to stay within a very narrow pH range, slightly alkaline, actually.
Yeah.
And our bodies are working hard to keep it that way.
Wow, so we've got our own internal pH balancing act going on all the time.
Exactly. And it's not just us. The environment has to maintain a pH balance too. Think about acid rain.
Acid rain, yeah, that's caused by pollution, right?
It is. When we burn fossil fuels, like coal and oil and gas, we release these not-so-friendly gases into the air, like sulfur dioxide and nitrogen oxide.
Yeah.
These gases, they get up into the atmosphere and react with water and oxygen and other stuff floating around up there. And what do they create? Acidic compounds like sulfuric acid and nitric acid.
And those are bad.
Yeah, and then it rains, and it's not just water falling from the sky anymore, it's all that acidic stuff too, hence the name. Acid rain.
So because of us, the rain is literally acidic. What does it do?
It's pretty harsh. Acid rain can mess up trees, make it hard for fish and other aquatic life to survive it, can even eat away at buildings and statues. It's like a slow and steady chemical attack.
Oh, wow. That's wild.
It really goes to show, though, even small changes in pH can have some pretty big consequences.
No kidding. I had no idea it was so impactful. It makes me think about, like, our teeth. I always hear acidic drinks are bad for your teeth. What's up with that? Is it a pH thing, too?
You know it. Remember all those hydrogen ions that acids love to release? Well, they can actually go after the enamel on your teeth. You know, that hard outer layer that protects them.
Oh no, so every time I sip on my orange juice or soda, I'm basically waging a chemical war on my teeth.
You're not wrong. I mean, our saliva does its best to neutralize some of that acid, but if we're constantly hitting our teeth with acidic stuff, it can wear down that enamel over time and lead to cavities.
Yikes. Okay, you've convinced me. I'm brushing extra well tonight. So we've got acids, we've got bases, and we've got pH. What a trio. What else is there in this chemical jamboree?
Well, we can't forget about the product of an acid and base getting together.
You mean when they neutralize each other?
Exactly. What happens when an acid and a base decide to call a truce?
They kiss and make up.
Well, sort of. They react, they neutralize each other, and in the process, they create a salt.
Salt. So we're going from sour and bitter to salty. Okay, I'm intrigued. Tell me more. So, wait, are we talking about, like, actual table salt here, the kind we sprinkle on our food?
We are. It all starts with a pretty simple reaction, actually.
Okay, so walk me through this. How do acids and bases make salt?
Well, it's called a neutralization reaction. When an acid and a base react, they kind of, like, cancel each other out. What do you get? Salt and water.
So it's like they shake hands and make peace, and then boom, salt. Amazing.
That's a great way to think about it. And just like there's a whole variety of acids and bases out there, there are tons of different salts.
I bet. But let's start with the basics, literally. What about table salt?
Ah, yes, sodium chloride, the celebrity of the salt world. But you know what? It's not just about making food taste good. Sodium chloride is used to make a bunch of other chemicals, too.
Really? Like what else can you do with a good old table salt?
Well, for one, it's used to make sodium hydroxide. You know, that stuff in drain cleaner.
Oh, wow. Yeah. I wouldn't have guessed that.
Right. And it's in some soaps, certain types of paper, even some medicines. Pretty versatile stuff.
Sodium chloride, you got my attention. What else we got in the salt family?
Another big one is baking soda, chemically. We call it sodium bicarbonate.
Baking soda. That's like the magician of my pantry. Cakes, cookies, deodorizing the fridge. It does it all.
And it's all thanks to chemistry. Baking soda is slightly basic.
Okay.
So when it reacts with acidic ingredients, you get those nice fluffy textures we all love in our baked goods.
So baking really is a science.
Absolutely. Oh, and we can't forget about washing sodium carbonate.
Washing soda, that rings a bell. I think I've seen it at the store, you know, like in the cleaning aisle, but I've always been a little afraid to ask, what's the deal with washing soda?
It's basically a powerhouse cleaner. Gets tough stains out of laundry, cuts through grease like nobody's business, can even soften hard water.
Wow, it's like the superhero of cleaning products.
That's a great way to put it. And to think, all of these amazing salts, from table salt to baking soda to washing soda, they all come from a simple reaction between an acid and a base.
That's incredible. I love how chemistry is everywhere we look, even in our kitchen. It's been an amazing journey through the world of chemistry today. From burning magnesium to baking cakes, we've seen how these chemical reactions shape the world around us.
And we've only just scratched the surface. There's so much more to discover in the fascinating world of chemistry.
That's right. But until next time, we'll leave you with a newfound appreciation for the atoms and molecules that make up our universe.
And remember, keep those brains bubbling with curiosity.
Absolutely. Thanks for joining us on this deep dive into chemistry. We'll catch you all on the flip side.